Hello students, I am Dr. Varun Mohan from ABES Engineering College, Ghaziabad. This is the lecture 5 of the lecture series of Unit 3 of Engineering Chemistry, BAS 101 and BAS 102. In the previous session, we discussed about basic concepts of corrosion, and today we shall discuss about some specific kinds of corrosion. These are the contents of today's lecture. First, we shall define what is passivity, and we shall discuss about the galvanic series. After that, we shall discuss about some specific kinds of corrosion, including bimetallic corrosion, differential aeration corrosion, waterline corrosion, pitting corrosion, crevice corrosion, and stress corrosion. After that, we shall discuss about a few questions which have appeared in the previous year's examinations. So let us first define what is passivity. Passivity is the phenomena by which a metal or alloy shows high corrosion resistance. It exhibits much lower corrosion rate than what can be expected from its position in the electrochemical series. The passivity arises due to the formation of very thin but highly protective film on the surface of the metal under specific environmental conditions, due to which it begins to act like a noble metal. For example, the metals like chromium, aluminium, nickel, and titanium, and some steel alloys which contain chromium show exceptional corrosion resistance in oxidizing environment due to the formation of insoluble oxide film on their surface. So this is how the passivity in the metals arises. However, a passive metal can be converted, it can turn into an active metal when environmental conditions are changed. As we have discussed in the previous slide, due to the formation of protective oxide film on the surface of the metal acquires passivity and behaves very differently from what we can predict from their position in the electrochemical series. Hence, a more precise and practical series should be prepared, which may give real and useful information regarding the corrosion behavior of metal and alloys in a given environment. Such a series is shown here in the table in the slide, and this is called the galvanic series. In this series, the metals are arranged according to their relative hierarchical position from magnesium at the active end to platinum at the passive end. The active end is also called the least noble end, and the passive end is also called the most noble end. The greater the difference in the position between the two metals in this series, the higher the chances that the corrosion of the anodic metal will occur. Now we shall discuss about a few specific kinds of corrosion. Among them, the first one is galvanic corrosion. It is also called as bimetallic corrosion or differential metal corrosion. As the name suggests, bimetallic corrosion means it should involve two different metals. It is caused when two different metals are in contact with each other, either directly or through an electrical conductor. When these are exposed to corrosive atmosphere, the metal which has more negative electrode potential more, more negative electrode potential, that metal will undergo corrosion. Actually, when we connect two different metals, they form a galvanic couple and a galvanic cell is established. That's why it is called as galvanic corrosion. The larger the potential difference between the two metals, the greater will be the galvanic corrosion. We can understand it with the help of an example. For example, if we take zinc and copper and those are kept in contact with each other in presence of electrolyte, then the zinc, which is having the lower electrode potential, will form anode, and the copper, which has higher electrode potential, will form the cathode. So here we have this zinc rod, which is, we can write it here as zinc rod, and it is in contact with another metal, that is the copper rod. So here this one is the copper rod. When those are exposed to a corrosive environment, this is the conducting solution. It can be any electrolyte. So when those are exposed to the corrosive environment, the zinc rod, which is having the position near the active end, will undergo corrosion. It will undergo oxidation. Whereas the copper metal, which is near the passive end, it remains passive and it remains protected. So zinc is active, so it forms the anode and undergoes oxidation, ejecting the electrons which move toward the cathode. The copper rod, which is passive, works as cathode here. So we can understand here the zinc is working as anode, which undergoes oxidation. That is the basically corrosion process. And copper remains protected due to its passive nature. So the reaction which is occurring at the anode can be shown as zinc solid is converted to zinc ions, which go into the solution and electrons are ejected. So this is how zinc undergoes corrosion here. The galvanic corrosion can be prevented by a few methods. Among them, the first one is avoiding the galvanic couple. Avoiding galvanic couple. It means we should choose the two metals in such a way that the potential difference between those two should be minimum. Even if we have to choose the metal, if we have to choose a couple of metals in such a way that they have a large potential difference, then galvanic corrosion can be prevented by avoiding the medium which is suitable for corrosion. So avoiding the medium suitable for corrosion. Another measure to prevent galvanic corrosion may be polishing the metal surface. So polishing the metal also retards this kind of corrosion. So these are the ways by which we can prevent the galvanic corrosion. The next kind of corrosion which we are going to discuss is differential aeration corrosion. It is also called as concentration cell corrosion. This kind of corrosion is also self-explanatory by its name. It occurs due to the electrochemical attack on the metal surface. When a metal surface is exposed to an electrolyte of varying concentration or of varying aeration. Differential aeration occurs when a metal surface is partially immersed in an electrolyte and the other part of the metal is exposed to the air. Under such conditions, the metal areas which are exposed to greater amount of air or oxygen, they behave as cathode. Cathode, which has a larger amount of oxygen, and the areas which are having lesser amount of air or oxygen, they work as anode. So they have lesser amount of oxygen. So we can understand because anode is responsible for oxidation. So the areas which are having lesser amount of oxygen will undergo oxidation, and this is the area which will suffer corrosion. For example, we can consider a zinc rod which is partially immersed in a dilute solution of sodium chloride. So this is our container in which we have filled a solution of sodium chloride. This is sodium chloride solution. In this solution, we have immersed a rod made up of zinc. This is zinc rod. The poorly oxygenated metallic part, which is in the solution, it becomes anodic. It works as anode and it undergoes oxidation. So the reaction here is conversion of zinc to zinc 2 plus and electrons are removed. And the area which is exposed to higher concentration of oxygen, it works as cathode. Here the oxygen takes up the electrons which are ejected from the anode. So this area works as cathode. And the reaction which happens here can be written as half O2 plus H2O plus 2 electrons. They generate hydroxide ions. The zinc ions from here and the hydroxide ions from here, the zinc ions from anode and the hydroxide ions from cathode, they combine to form the corrosion product. So the corrosion product here is zinc hydroxide. Accumulation of any kind of dirt, sand, or scale on the metal will also promote this kind of corrosion because that area which is covered with the dirt or sand will become poorly oxygenated. This kind of corrosion is localized on the metal surface. So it is a localized attack. It is arising from a localized attack on those areas which are oxygen deficient. Differential aeration corrosion ultimately leads to the deep cavity, and if it is not prevented, then ultimately it may lead to the pitting corrosion. The next kind of corrosion is waterline corrosion. The waterline corrosion is a special case of differential aeration corrosion. When we take water and store it in a steel or iron tank for a long time, we can observe some amount of rust begins to accumulate just beneath the level of the water. This is called waterline corrosion, and it occurs due to the difference in the aeration at different parts of the tank walls. For example, we may draw it like this. Suppose this is our water tank, which is made up of iron or steel, and water is stored here for a long time. So this is water, and this is the steel tank. This is the water level. If the water is held for a long time, then we can observe resting just beneath the water level. So this is the rest here. This is the rest. It happens because the area above the water line, is highly oxygenated, and the area below the water line is poorly oxygenated. So the poorly oxygenated area, this area begins to work as anode, and this area, which is highly oxygenated, this begins to work as cathode. So due to the difference in the aeration, differential aeration corrosion happens here, and it leads to the waterline corrosion. So this area, which is now working as anode, causes the oxidation of iron to occur. So the reaction here happens as iron is converted to iron 2 plus, and 2 electrons are removed. These electrons are taken up by the oxygen at the cathode, and the reaction which happens here can be written as half O2 plus H2O plus 2 electrons ultimately give rise to the formation of hydroxide ions. So the ferrous ions are generated at the anode, and hydroxide ions are generated at the cathode. These combine to form the corrosion product. And when we see iron 2 plus combines with hydroxide to form ferrous hydroxide, this ferrous hydroxide under oxidizing environment in the atmosphere converts to ferric hydroxide, which leads to the formation of rust. This kind of corrosion can be prevented by the use of anodic inhibitors or by the use of anti-fouling paints. About them, we shall discuss in more detail in the next session, where we shall discuss about the protection from corrosion. The next kind of corrosion is pitting corrosion. The pitting corrosion is a localized corrosion. It is localized corrosion which results in the formation of pinholes, cavities, or pits. It usually takes place when there is a crack in the outer protective oxide layer on the surface of the metal. The crack on the protective film works as anode, and the rest of the oxide layer, which is intact, works as cathode. Since the area of crack is very small, the anode is very small as compared to the cathode. So because of very small area of anode, there will be severe corrosion, which will lead to the formation of a small hole or pit in the metal. It can be seen with the help of a diagram. Suppose this is the iron bar, and this iron bar had a crack here in the outer oxide layer. So this area will begin to work as anode and it will undergo corrosion. The rest of the area will work as cathode, which is having more access to the oxygen. So corrosion occurs here and the metal undergoes loss of its weight and loss of its strength. So this area is working as anode, which is having less amount of oxygen. So iron here is converted to iron 2 plus and electrons are removed. This area, which is now working as cathode, it is more oxygenated, and here the reactions which take place can be shown as half oxygen plus water plus 2 electrons convert to the hydroxide ion. So due to the corrosion product will accumulate here in the form of rust. Now rust is accumulated on the surface, which further screens the bottom of the pit from the oxygen. So because of this screening, the corrosion, the rate of the corrosion will further increase because it has now uh, less access to the oxygen as compared to the previous condition. In this case, the pitting corrosion can be minimized as usage of pure metals. It means the impurities in the metal should be avoided. Another measure to prevent pitting corrosion is by polishing the metal surface properly. Designing the metal articles judiciously can also be one of the measures to prevent the pitting corrosion. This was about pitting corrosion. Now we shall discuss about the crevice corrosion. The word crevice refers to any kind of gap or crack. So crevice corrosion may be defined as the corrosion occurring at the region of contact of metals with metals or non-metals. For example, the corrosion occurring at the crevices between different metallic objects like bolts, rivets, nuts, washers. These are the examples of crevice corrosion. So crevice has very narrow area. It has lack of oxygen, and because it has lack of oxygen, less access to oxygen, it acts as anodic region under the corrosive environment. Whereas the exposed area acts as the cathode. Hence, the corrosion occurs at the crevice because crevice is working as the anode here. The crevice corrosion can be understood in terms of the concentration cell core effect. For example, it can be shown with the help of a diagram. Suppose this is a metal structure, and here we have a bolt, a nut or a bolt. So these areas are having very narrow dimensions because of lesser amount of oxygen available here. This area undergoes corrosion. Similarly here, due to the lack of oxygen, it works as anode, and this area undergoes corrosion. So this is the rust here, and this rust is due to the uh, anode formation in this area. So this is anode, which is less aerated. This is cathode, which is more aerated. So in those areas where nuts, bolts, or screws are there, the area which is less aerated becomes as anode, and the area which is exposed to the atmosphere or exposed to the oxygen, that works as cathode. So the anode undergoes oxidation and it leads to the formation of rust. Deposition of dirt or debris will accelerate this type of corrosion because it will restrict the supply of oxygen to the underneath area. Another kind of corrosion is the stress corrosion. The stress corrosion is also called the stress cracking. It takes place due to the combined effect of mechanical stress and the corrosive environment. It means both are necessary for the stress cracking to occur. If the metal object is under stress and it does not get suitable corrosive environment, then also corrosion will not occur. And if the metal is not having any uneven stress, then the corrosive environment causes the corrosion, but it will not be called as the stress corrosion. We know when the articles are fabricated, metal articles are fabricated, they undergo several processes like rolling, drawing, and annealing. During rolling and drawing and If the annealing is not done properly, the metal may have uneven stress. In such cases, the metal areas which are under stress, when those are exposed to the corrosive environment, they begin to behave as the anodic part, and rest of the area which is unstressed works as the cathodic part. So anode is in that area which is stressed, and cathode is that area which is unstressed. So when suitable corrosive environment is given, the anodic areas undergo corrosion. The stress corrosion is unpredictable in nature. It means it may appear suddenly, it may cause sudden cracks to appear without any previous deformation in the metal article. It is important to note that stress cracking takes place only in highly selective environment. For example, if we talk about the brass objects, the objects which are made up of brass can show corrosion cracking only in presence of traces of ammonia or the amines. So the stress corrosion is highly specific in terms of the corrosion environment. We can understand it with the help of a diagram. Suppose this is our metal object, and here we have different grains. So this is grain A, and this is grain B. During its fabrication, these areas, if these are unstressed, if these areas are unstressed, and this is the stressed part, this area, which is the grain boundary, this is the stressed part. In that case, it will form anode here, and this area will begin to work as cathode. So because of anode and cathode formation, the corrosion current will begin to flow, and it will lead to the stress corrosion. Now we shall discuss a few questions which have appeared in the previous year examinations. Question is, why does part of the nail inside the wood undergoes corrosion easily? Suppose this is a piece of wood, and nail here is shown like this. This area of the nail is inside the wood. Now we have discussed that the part which is exposed to the air will begin to work as cathode, which is having higher amount of oxygen. So it has more oxygen or more amount of air. And this area is having less access to the oxygen. So this area will work as anode because it has less amount of oxygen. We know the oxidation occurs at the anode. So the iron will convert to iron 2 plus, and electrons will be ejected. These electrons will be taken up by the cathode, and here oxygen will take up these electrons to form the hydroxide ion. So because the oxidation is occurring at the anode will undergo corrosion and it will undergo rusting. That's why the part of the nail inside the wood undergoes corrosion easily. So at anode, the reaction we have shown, it is iron converting to iron 2 plus and 2 electrons. This is oxidation process. At cathode, half O2 plus H2O plus 2 electrons convert to 2 OH minus. This is the reduction process. And the iron 2 plus and hydroxide ions will combine to form ferrous hydroxide, which under oxidizing atmosphere converts to ferric hydroxide, leading to the rust formation. So because the oxidation process is occurring at anode, corrosion is happening at the anode, and that's why the part of the nail inside the wood undergoes corrosion. Discuss the mechanism of electrochemical corrosion of iron with evolution of hydrogen. This part of the question we have discussed in the previous lecture. What will happen if a zinc rod is vertically half submerged under water? The same question is also asked in another way. Explain why a pure metal rod half immersed vertically in the water starts corroding at the bottom. So this can be explained in terms of differential aeration corrosion. Suppose this is the container having water, and here we have a rod of any metal or zinc. As asked in the first question, it is zinc rod. In second question, it is given as a pure metal rod. So this is the metal rod. Some of its part is submerged in the water up to here, and some of its part is exposed to the atmosphere. The area which is exposed to the atmosphere, it works as cathode, and the area which is submerged in the water, because it is having lesser oxygen, it will work as anode. So cathode here has more oxygen, more aeration, and anode here has less aeration. The area which is having less amount of oxygen works as anode. The area which has higher amount of oxygen works as cathode. At anode, the metal will undergo oxidation. So metal will form the metal ion, losing some electrons. In case of zinc rod, it will work as the anode, and it will form the zinc ions, losing some electrons. So in that case, this reaction can be written as zinc converted to zinc 2 plus ions, losing 2 electrons. These electrons are taken up by the oxygen at the cathode, and the reaction happens as half O2 plus H2O plus 2 electrons convert to the hydroxide ion. The metal ions and the hydroxide ions, they combine with each other to form the corrosion product. So what will happen if a zinc rod is vertically half submerged under water? We shall write that the part of the metal which is submerged in the water will undergo corrosion due to differential aeration. Explain why a pure metal rod half immersed vertically in the water starts corroding at the bottom. We shall write because the uh, part of the metal rod which is immersed in the water has less access to the oxygen. Less access of oxygen converts it to the anodic portion, and anode is responsible for oxidation. So the submerged part undergoes corrosion. These are the suggested references. Thank you for attending this session.